Testing, testing, 1, 2, 3, testing, testing. Okay. Yeah. Hello, everybody. Welcome to this, our lecture for Friday, the one before the weekend. Huzzah. I hope everybody's doing all right today. If anybody would mind just... Oh, I don't think I actually made the... Here we go. Lecture chat. There we go. All right, if somebody wouldn't mind putting some stuff in there to indicate to me that you guys are alive, that would be awesome. So, yeah, might as well get right into it. Cool. So, yesterday we were talking about bitwise operators. Bitwise operators, of course, being operations that occur according to bits, rather than anything that would make sense in a more arithmetic or algebraic mindset. You know, us human beings, we've been trained from a very early age to think of numbers, you know, in the decimal system and, you know, according to decimal digits. But of course, a computer only knows binary digits. So these are roughly operations on binary digits. But anyway, so we talked about AND, we talked about OR, and we talked about XOR. So let's move on to left shift. So, the left shift operation, which is two less than symbols, moves the bit values of the number x by the number of bits y to the left. So x is what you're moving, y is how much you're moving it by. We consider left to be towards the larger place values in big endian systems, which are most of them. So a big endian system is a system where the bits that occur on the left side of the number are larger than the bits that occur on the right side of the number. In terms of hardware, this corresponds to bits with lower memory addresses within the same integer or within the same number are higher place values than bits that occur later on with higher memory addresses. This should be reasonably, you know, straightforward for you, since this is, roughly speaking, how decimal numbers work. So anyway, from a pragmatic standpoint, this is precisely the same as multiplication by 2 to the power of y. So, if you want to perform multiplication by 2 to the power of y, and you don't want to use the power function or get involved with exponents at all, you can actually substitute a left shift operation, and it's a lot more compiler efficient to do that. That's the thing about these bitwise operations, is they are, generally speaking, very, very fast, and they don't take much memory, and they're just, bam, you're done. So left shift. This is an illustration of left shifting by 1. You notice we have the number 011001110, that'll be x, and we are left shifting by 1, so y would be 1 in this case. So the 0 goes from the 0th slot to the first slot, first to second, second to third, third to fourth, etc., etc. The bit that's in the maximal position is, in fact, just dropped. It is deleted. It is overwritten. It is not recorded. And at the lower end of the number 0 is slotted into the position. So if you imagine that what it's going to do is going to wrap around the digit to the other side, that's not actually That's not actually what it's doing. You could totally design a circuit to do that. It would actually not be too difficult to just, run a wire around and then feed it back into the register over here. However, that's not what left shift means in the context of a computer, even if you can design a circuit to do that. Nobody said anything in chat yet. Aw. You guys are really tired, I guess. Boop, ba-doop, ba-doop. Can you guys see that? Is it, like, too fuzzy? Man, that is terrible. Yikes. Well, maybe it would be best to follow along in the slides that I recently uploaded to Avenue, then. So, similarly to left shift, you also have a right shift operation. It's the exact same gosh darned thing, but in the opposite direction. We are, instead of moving the bits, shifting the bits to the left, we're shifting them to the right, hence right shift. Just like the last one, but in the reverse direction. From a pragmatic standpoint, this is precisely the same as division by 2 to the y with truncation. So, of course, obviously it's not saving any decimal places because we're dealing with, integers here. I mean, it's certainly possible to apply these bitwise operations to data types that are not integers. However, because the integer format is so straightforward, it really is best applied to a very simple data format. If you tried to apply these types of, if you tried to apply a shifting operation to something of a, like a float or a double type without, God only knows what it would do, it would, end up taking things from the extreme end of the mantissa and putting it in the front of the exponent and maybe doing weird stuff like that. I don't know. But anyway, the same operation, same deletion, this time of the least significant bit, and the same introduction of 0 to the most significant bit. So there you go. Shifting operations. So, let's talk about 1's complement. The complement operator, which is the tilde, which is the one that's above tab, shift, and the button above tab on your keyboard, it simply takes each bit and flips it. So, if we have 00110011, then the complement of that would be 11001100. If you're the type of nerd that likes to squeeze either speed or power efficiency out of your code, bitwise operations typically take far less circuitry and in some cases time than algebraic operations. So there you go. Any questions about that so far? You guys are alive, right? I'm in the correct... I haven't heard anything on chat yet. Hello. So, here are, just to sort of hammer home bitwise and the idea of it, here are some common arithmetic operations expressed in bitwise arithmetic. So, let's talk about addition. If we were to create a function to add two numbers without using the actual addition operator, using only bitwise addition, you have to think about how addition works, right? When you're doing addition on decimal arithmetic, you start in the least significant column and you work your way up to the most significant column. You add those two numbers together, and if there's anything to carry over, you sort of write it above and then add that to the next sequence. So you can tell if you need to carry something by whether x and y are both set in binary arithmetic. If you were to add binary numbers, if you add 0 to 0, you get 0. If you add 1 and 0, you get 1. 0 and 1, you get 1. But if you have 1 and 1, then you get 0 in that place, place value, and then you carry 1 to the next. So you can tell whether or not you have to carry numbers by the bitwise AND operation on x and y. There we go. So we then calculate x by taking the XOR operation, because remember, if the two digits are distinct from each other, then 1 is the result. So that is definitionally, that's the XOR operation. Nothing? Nobody's saying anything today? Am I in the right? Whoa, uh-oh. Sorry, I just had to check the connection there. So, anyway, so we assign this variable to hold the carry values. We calculate what the carry values are. We assign x to the, we make x the sum with the carry value, with the carry values kept separately, and then we assign the carry values to y, but we left shift it up by 1, right? Because in order to apply the carry values to the next place value, you have to shift it up, right? So you repeat this until y is equal to 0, which means that you continue this until there are no more carry values, right? So once you have eliminated all the carry values, you then return x. So there you go. And the procedure for performing subtraction using bitwise operations is pretty similar. Rather than carrying values, you're borrowing values. So you can tell whether you need to borrow a value if, assuming we're subtracting x from y here, if x is 0 and y is 1, right? So if it's 0 subtract 1, then you got to borrow. But otherwise, you don't. You don't have to worry about it. After that, x is calculated once again as the XOR operation of x and y. So, yeah. And then the borrow is made into y and shifted again, and again we repeat that procedure until no more borrowing is required. So there you go. That's some bitwise stuff. So let's talk about 2's complement, which is more bitwise stuff, but not the operators this time. Have you ever wondered how integers store negative numbers? The answer is in the title to this slide, 2's complement. Your computer interprets any integer with a leading 1 to be a negative number, so long as that integer doesn't have the unsigned tag. So, D, remember, is interpreting as an integer, and U as an unsigned integer. If we have the maximum value that an 8-bit integer can be, expressed in hexadecimal, then we get -1 if we interpret that as a signed integer, and what is it? 4,294,964,295 if you interpret that as an unsigned integer. If we take a look at FFFE, which is 1 minus the maximal value that can be stored in an integer, in an 8-bit integer, we get a -2, whereas on this, as an unsigned integer, we have reduced by 1. Technically, in both cases, we have subtracted 1 from the total here. It's just, in one case, the magnitude is increasing, and in the other case, the magnitude is decreasing. But that's sort of the way that you can think about it, is the negative numbers sort of count down from the maximal value, and the positive numbers count up from the minimal value. Tumbleweeds. Can you guys not log in? Like, what's the... Like, I should be seeing something here, yeah? Posts, files, assignments, grades. The frick is going on? Okay, I have to... Pardon me for a moment. I gotta check... I'm gonna turn the live chat on just for a moment so that you guys can, like, tell me if the other one isn't working. Okay. I've just activated the live chat. If someone wouldn't mind letting me know if the chat on Microsoft Teams is working or not, I would appreciate it. Because, you know, normally when I say, hey guys, could someone please indicate to me that this is actually working, I get at least someone saying something. So, yeah. Refresh Teams. I can't see it. You're in it. Okay. Thank you. Thank you. Oh my goodness. Okay. So I only see 3 here. Chats? Okay. 18 replies. There we go. Okay. Hello. Yes. So, to go... I apologize, guys. Okay. I feel much better. I feel like I'm not talking to a brick wall. So, is one's complement is not two's complement. We're going to see what two's complement is. And, yeah, one's complement is just a NOT gate, but it's applied to everything. Yeah, I didn't think that was sufficiently... I didn't think you needed a... Yeah. Yeah, it wasn't updating for me. Well, I mean, you could see. Okay, cool. Right. Doop, 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 doop. Cool. All right. Anyway, so two's complement. If you perform the two's complement operation on a number, it flips the sign of that number. And this is how you do it. First, you take the bitwise complement. Second, you add 1 to the number. Third, profit. The same procedure changes a negative number into a positive one. So, for example, if we have an integer value hexadecimal AAAAAAAA, in terms of signed integers, that is negative 1,431,655,766. If we take the complement of that value, we get, as a signed integer, 1,431,655,765, and then if we add 1 to that, we get 1,431,655,766 again. Notice the sign is flipped. So that's the 2's complement operation. Complement, add 1. So you may be asking yourself, okay, but why? Why would we do this? Why is this necessary to perform negative arithmetic? Why does this happen? Well, I'm so glad you asked. We're going to go through an example to show you that when a number is in 2's complement form, you actually don't require any modification to the procedure for various arithmetic operations, such as addition, in order to have the answer come out correctly. If that weren't the case, you would need to have some way of telling whether or not the number was positive or negative, and then have different circuits that calculate addition based on whether or not it's a positive or negative number. But because of 2's complement, you actually can use the same circuitry for both, or the same algorithm, the same procedure, for both addition between purely positive numbers, addition between positive and negative numbers, and addition between negative numbers. All of these get to have the same procedure. So, during decimal addition, we go through each pair of digits, starting with the least significant, and add the digits. If the result is greater than 1 digit, that result is added to the next place value. The procedure in binary is exactly the same. If I had a chalkboard right now, I would be doing this on a chalkboard for you guys. But because we don't have a chalkboard, we're just going to have to use slides, unfortunately. So if we have 21 plus 19, we've got 1 plus 9 is 0, carry the 1. 1 plus 2 plus 1 is 4, so the answer is 40. If we've got 7 plus 2 in binary notation, that's 0111 plus 0010. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is plus 0 is 0, carry the 1. 1 plus 0 plus 0 plus 1 is 1. Therefore, the correct answer is 1001. So there you go. There you go. Oh. Ha ha ha. That's a cool pumpkin. I like that pumpkin. So, okay, but why? So, consider the following example. If we have the following number, and we're going to keep it to 8 bits because, you know, nobody wants to have, like, all 32 bits of a 32-bit integer on this slide, you know? So we'll keep it to 8 bits. But negative 14 in 8-bit, as an 8-bit integer is 11110010, and 25 is 000110001. So, if we perform the addition operation, 0 plus 1 is 1, 1 plus 0 is 1, 00 is 0, 0 plus 1 is 1, 1 plus 1 is 0. We then carry the 1, 1, 1, 0, carry the 1, carry the 1, carry the 1, and then we have 1 left over. So the thing about it is that the final carry is truncated. It's dropped because that exceeds the storage capacity of the integer. So this guy is removed. And because he's removed, the value here is 11. And 25 plus negative 14, if you are a math whiz such as myself, that is, in fact, 11. So there you go. 2's complement works. Awesome. Since the overflow digit is lost, this can be said to work. There we go. Cool. So are there any questions about bitwise or 2's complement or anything of that nature before we move on to our next topic? The next topic is back to structures and algorithms and graphs and stuff like that. Okay, I'm gonna assume everybody's cool with that information. It is pretty, it does look a bit elementary school, but that's okay. So, now for some stuff that's very not elementary school. Let's talk about graph theory. Graph theory, graph theory, graph theory. You'll be happy. Oh, I do have a question. Ha! Teams connection test. Yes. There should be, like, an indicator somewhere that you have DC'd. Maybe it was, like, here or something. I don't know. Who knows? Anyway. So, let's talk about graph theory. In order to solve problems, we need mathematical models which we use to express those problems. For example, algebra is a mathematical model. It turns out that it's quite a useful mathematical model. That's why it's taught. It turns out that if you're trying to come up with a way of reasoning about physical reality, let's make it more concrete. Let's say motion, the equations of motion. If you're trying to come up with a mathematical model that describes the motion of objects, it turns out that it's useful to have calculus as a model for that calculation and that prediction. We're going to talk about an abstraction that is commonly used in computer science, and it's called the graph theory. And we're not talking about plotting charts. We're not talking about histograms or scatter plots or anything, normal distributions or anything that might be related to statistical science. This is more highly related to set theory and abstract algebra. So this is going to be a little bit beyond, like, some of the symbols here are probably things you've never seen before, but that's okay, because you're seeing them in your second year instead of wondering what they are when Dr. Wassing uses them in third year. So we're gonna have a nice rough introduction. We're gonna have a nice gentle introduction. Ooh, 3 blue, 1 brown has some cool graph theory videos. So some of you have heard of graph theory. How many of you guys have never heard of graph theory before? Just out of curiosity. But anyway, so graphs, defined in this sense, are a collection of vertices with a collection of edges. This is a way of modeling objects and the relation between objects. So, and we're going to see examples. The graph is defined mathematically as the ordered pair G is equal to VE, where V is a set of nodes or vertices, and E is the set of edges, conforming to E is a subset of pairs x, y, where x and y are elements of V, and x does not equal y. So this means that an edge is defined as a pair of vertices where the two vertices may not be the same. Sometimes that's not a restriction. Sometimes you can have nodes that point to themselves, especially if you guys start getting into state machines. But yeah, okay. Let's see. Don't worry about think you should have. Don't worry about that. That's when you guys take your algorithms course next semester, it's probable that you'll start working with graph theory. So I just wanted to give you a taste for it, because it's always easier to understand, like, if you've been scaffolded into the knowledge a little bit. So this is like, so let me put it to you this way. C courses will often talk about data structures without introducing the concept of graph theory first, and because of that, you don't have like the sort of more formal mathematical model that you need to discuss them in a more rigorous manner. And when you do end up needing the mathematical model for some, future stuff, it's going to be useful to have seen it before. So that's why we're doing it. So anyway, once I show you what a picture of what a graph looks like, you're going to be like, oh, one of those. So here, this is a graph. Oh, one of those. So this is a graph. We've got a set of vertices, 1, 2, 3, 4, 5, and 6, and we have a set of edges. 6, 4, 4, 5, 4, 3, 3, 2, 5, 2, and 5, 1. It doesn't matter what order you put these in here. It doesn't even necessarily, you don't even necessarily have to write it out. Although, this can be a useful mechanism for expressing a graph in a computer. These are sets, right? So bring your set theory knowledge in to this realm. It doesn't really matter what order you put these in. What matters is that they're all there and that there are no duplicates. So, questions and comments. So, we've had two recommendations. Two recommendations from one person of a YouTuber called 3Blue1Brown. I can't vouch for this person myself, as I have never seen any of their videos, new to me, but it's entirely possible. I'll probably check out a video, see if it's cool. Anyway. So yeah, it's not actually that difficult a concept, but at least in its simplest iteration. This is the simplest, this is the most general form of what a graph is. But the reason we're introducing graphs and we're talking about graphs is that once we start talking about data structures, we can very often come up with a data structure that can be expressed as a graph. So, okay. Can vouch. Okay, so we've had a person vouch for that YouTube channel. Cool. So, amazing visualizations and several math concepts. Okay, so 3 recommendations for this guy. I'm going to definitely have to check it out then. So, directed graphs. The previous slide presented a graph in its most general form. If we apply properties to graphs, we get some interesting structures. So, this is a graph with no mathematical properties applied to it, except that it's a set of vertices and a set of edges. Right? In this graph, which of these numbers comes first when we declare an edge doesn't matter. This is what's called an undirected graph. However, if the order in which these guys are declared in the list of edges matters, you end up with a directed graph. This is what a directed graph looks like. So basically, all we're doing is we're taking the edges and we're turning them into arrows. If the ordering of the numbers in the edge pair matters, the graph is directed. Simply put, the graph has arrows instead of straight lines. We also have cyclic versus acyclic graphs. So a cyclic graph contains cycles. If it is possible to return to any node by following the edges of a directed graph, then the graph is cyclic, and the path that you take to return to the node you started from is a cycle. Otherwise, the graph is called acyclic. A being the prefix that means not. You know, like aseptic technique means technique which is not septic. But anyway, so here are some examples. This is a directed cyclic graph because you can see from this node at the bottom, we can reach this node again by going up, across, and then down again. This is actually true for any node on the graph, but it's not necessary to be able to reach any node from itself in a cyclic graph. All that a graph requires is one cycle in it to be considered cyclic. You also have directed acyclic graphs. So this is an acyclic graph because you can see it is not possible to return to 8 from by following the arrows. It's not possible to return to 11. It's actually not possible to return to any of these nodes via the arrows. Graphs can have a lot more properties than this, but this is sufficient for this point in time. In the context of C programming, we can make nodes with structures. If our structure contains a pointer to another structure of the same type, i.e. a self-referential pointer, this can be considered an edge. So, and we're going to see how this works on a particular type of data structure called a linked list. Linked lists are classic C material. If you have studied C and you have not covered linked lists, then you have not studied C. Boop. Boop. So, a singly linked list is a graph where each node points to one other node, or no nodes, and no node is pointed to more than once. This effectively creates a linear data structure, such as this. You see, it's a linear data structure. It's just a sequence of nodes that point to each other. This is similar in many respects to our old friend the array, but there are some key differences that we're going to go over. This is actually how languages such as Lisp and Haskell store lists, their primitive native aggregate data type. So whereas arrays are the primitive native aggregate data type in C, the same purpose is served by a list in Haskell and Lisp. Lisp actually stands for list processor, by the way, and Haskell is kind of the successor language to Lisp. But these guys use this type of data structure, a singly linked list, by default. So there you go. So, the nodes of the graph can be expressed as objects of a structure type in C. All we need to do is take an existing structure and add the self-referential pointer next. So, if you remember our structure from before with the name, email, and pinball score, we can turn this into a linked list, structurally speaking, by just by adding one self-referential pointer. This doesn't... So, the difference here between C and a language like Python is that in order for this to actually be used like a linked list, you have to access these structures with functions that treat the structure like a linked list. So it's not just the fact that you've added a pointer, a self-referential pointer. You also have to enforce a data policy, and that data policy must be, each node in the list points to the next one, and the one at the end of the list points to null. So the last element in the list points to null. You, the C programmer, are required to enforce this yourself, just like you have to enforce array out-of-bounds problems. So, as with many things in C, there are no free lunches. If we wish to refer to a singly linked list in main or one of our other functions, we need only a single node from which we can access the rest. Struct SLL node linked list. That's how you would declare this thing, because we can if we have this first node, we can always access the rest of the list by following the pointers. So, if we apply our data structure to the singly linked list structure, we get the following. You can see we have these, the nodes, rather than just being sort of these silly little labeled things, we now have, blocks of memory that can hold values and also hold a pointer to the next block of memory that holds values, which is cool. The more information that is contained in the structure, the more advantageous it is to organize it in this manner, for reasons that we're going to see shortly. If you wish to pass the first node by reference to a function, keep in mind that within the function you will have to dereference the argument to get the first node's data. So, again, if you, the larger the record becomes, the more inclined you should be to pass it by reference rather than passing it by value. Remember, if we're passing by value, then everything that's in the structure has to be copied into the stack frame for the new function that's being invoked. And if we have a lot of data in there, it takes time to copy it. So this is especially true if your record is full of aggregate data types, such as, strings and things like that. So anyway, so yeah, that's how that works out. Are there any questions so far? Any questions? Okay. So, why go to all the bother? This seems like a lot of work just to make something that functions roughly like an array. This is very similar to an array of the structured type. Why would we go to all this work? Well, because the list is not stored in contiguous memory. So, when you are adding an element to a linked list, as opposed to adding it to an array, you don't have to reallocate the entire array, copy all of the information from the records into the new memory space that's been allocated, and then, populate the thing at the end that's the new one, the same way that basically the way that the stack question worked on the midterm. Instead, you can just allocate a new space in memory the size of a single structure and then point to it. You can, in fact, dynamically grow or shrink the array without having to copy it, this saves a whole bunch of time. Also, because the next node is indicated with pointers, these pointers may be modified. This means that a linked list may have elements inserted in it without having to move any of the other elements in memory. So, if you think about trying to insert, let's just do like a regular array, and let's say we have a sorted array. Let's say we have a sorted array and we want to insert an element into that array in such a manner that the array maintains its sortedness. You have to find the position that the element would need to be inserted at, and then you have to take the whole rest of the list and move it one memory cell over to make room for this new element that you're sticking into the middle of the array. With a linked list, you don't have to do that. All you have to do is allocate new memory space for the new whatever it is that you need to insert, and then you just update the pointers. Update the pointer of the thing that should be pointing to it, and copy the old value of that pointer to the pointer of the new node, and then it'll point back into the list, and you can continue your list as you were. Correspondingly, it's also easier to delete an item out of a linked list than it is to delete one out of an array. If you were to remove any particular element in an array, you would have to move the entire array down one slot in order to, fill the gap. Whereas, in linked lists, all you have to do is free that memory space, move the pointer that was pointing to it to the thing that it was pointing to, and that closes the gap. And, you no longer need any while loops to do that. You can do it in single operations. As soon as you've found the element, though, that's the trick. Boop. Does this mean you can make branches and adjusting the pointers to choose certain branch if you want to flip between two lists or the same beginning or the middle at the end? You are getting ahead of me, Anthony, a little bit. What you're describing is a tree. And we're going to talk about trees, but in the next class we're going to talk about trees. But yeah, so this type of data structure, you can imagine if you had two pointers on the end here, say a left and a right, then you could have these guys point to, well, it would be a tree structure. Let me see if I can, binary tree. Let me see if yeah. So you would end up like with a structure looking something like this, right? That's a tree, and that's totally 100% possible. Although what we're doing with structures and pointers right now is somewhat facile, you can do holy butts worth of crazy and interesting things with these types of structures. And, like, if rather than a single pointer, you made this an array of pointers that could also be dynamically allocated, you could, in theory, also have nodes that could point to an arbitrary number of other nodes, which would implement graphs in the manner we were seeing in, like, this slide, or this slide. But anyway, yeah, so right now we're just doing, like, singly linked lists, though. So, as with most other things in engineering, though, storing your data inside of a linked list as opposed to an array comes with some trade-offs. So there are some drawbacks as well as advantages. Some things are made much easier, and some things are made harder. For example, you can no longer access any specific element in a linked list via direct indexing and pointer arithmetic. So in an array, obviously, all you have to do is add some number to the pointer that points to the array and dereference it in order to access any particular element in the array. In a linked list, because the individual nodes are not being stored in contiguous memory space, you can't actually perform pointer arithmetic in order to access any particular node. What you have to do is you have to follow the pointers. Follow the pointers until you've followed a number of pointers equal to the depth you're looking to get into the linked list. So there you go. How would we access the element before the current element without adding a pointer to the previous element? Oh my god! Omar, that's the next slide. That's actually the next... So the answer to that is you add one. You create one called previous. So yeah, that's the problem with a singly linked list, is that it's only traversable in one direction. If you want it to be traversable in two directions, then you need to make it a doubly linked list. But that's gonna be our time for today. Have a nice weekend, everybody. We'll talk about doubly linked lists and trees next time. So if you guys have questions, please ask your questions. I will answer them. And yeah. But if your question is, please teach me everything you're going to teach me next class, I'm probably going to say no. Well, that's not true. I'll probably say yes, but I won't have slides to back it up. So there you go. Does the programming class next term consist of extensions of these topics? It's hard to say. I haven't actually looked at the curriculum, but I can let me take a look at the course description, and maybe that will do. Registrar. Has anybody got a course code for me? What's the course code for this course that you guys are... I suppose I can look it up in the mechatronics program thing. level 2. Wow, they're making you guys take economics? Did they move that out of 4th year? They did move it out of 4th year. That's crazy. When I took that, that was in 4th year that you took that, and everybody knew it was a bird course and nobody paid attention. Yeah, 2MD3. Data structure, algorithms, and language concepts for mechatronics. Oh, okay. Shut up, me. There we go. Oh my god. Stop. There we go. Advanced programming with emphasis on embedded systems. Programming specifications, pre- and post conditions, loop and data type invariants. Use of tools to demonstrate correctness. Selecting data structures for implementation of mathematical abstractions, finite state machines, automata and languages, lexing and parsing, algorithm analysis, time and space, modeling of graphs, relations, corresponding algorithms. So modeling of graphs, relations, and corresponding algorithms, that would be the stuff that would be an extension of the stuff we're currently doing. Interesting that they're throwing like parsing and lexing in there. So finite state machines and automata are also a thing that can be expressed using graph theory. A finite state machine is basically a graph where one of the nodes is like the point in the program that you are currently at. So if you take a graph and a directed graph and you sort of make it instructions instead of data, and you make the edges have like conditions to go from one state to another, then you've got a finite state machine. And automata are a very similar concept. But yeah, that seems, I don't know, it seems like, yeah, a certain amount of it. The pre- and post-condition stuff. Seems like they're doing, like, some formal method stuff with you guys as well, which, you know, will serve you usefully when you hit 3K04. 3K04? Yes. Yep. Anyway, yeah, that's, this course, 3DX4, I TA'd that for like 5 years. Most of the labs in that course were either heavily revised by me personally or written by me from scratch, unless they've, you know, it's been a while since I was working on it, but yeah. Nostalgia. Anyway, I'll let you guys get to your next class. Probably most of you have already anyway. Thank you very much for your time and attention, folks. Talk to you soon.